All right, welcome class. We are going to look at another example here. This one is example 4 for my Physics 1 class, or it's example 3 for my Honors Physics class. So the crate that they're talking about here, from a previous example, I did actually solve that beforehand. However, for those that didn't watch that, you should note that the crate had a mass of 350 kilograms from a previous example. So instead, that time, we were taking the crate and we were moving it across the floor like this. The difference here is that this one is being lifted. So therefore, it's going to start at some level and it's going to be raised up to some new height. And then, in fact, in this case, it's going to be 3.2 meters. Also, I note here that it's moving at a constant speed. So when I see constant speed, I'm thinking acceleration equals 0. Another thing I want to think about is that the net force has to be 0, and this is only accomplished if the forces balance. All right, so these are things that I'm thinking when I see the words constant speed. I'm thinking about 0 acceleration, net force of 0, and forces being in balance. So as far as what we're trying to find here, we are trying to find the work done on the crate by the object that lifts it, whatever that object might be. And second of all, we're finding the work done on the crate by gravity as it's being lifted. Okay, so to show I understand here, I've drawn two different pictures. One is the free body diagram of this object, and basically what we have there, of course, is the Earth pulling downwards on it. That's what we know as the force of gravity. So there we have that. And then I'm going to just call this an applied force, so force A is on the crate by some unknown object. Again, what the object is doesn't really matter for this problem, but that's what it is. Also, as it moves upwards, it does move upwards this 3.2 meters with a 0 acceleration. Once again, that means that this force down and this force up have to balance. The net force of these two is 0, or another way of saying that is this downwards force has to be equal to the upwards force. At least the magnitudes are. Of course, opposite directions, but equal magnitudes. So basically, what I'm looking at here is the kinetic energy. Let me zoom in on this right here. Basically, the kinetic energy is going to remain constant through this problem. Okay, so this is a constant value. We don't know what that value is because we're not told how fast it goes. We just know that it's constant. So the work that's being done here does not actually go in to changing our kinetic energy in any way. The work that we're being done, which is what we're trying to find, must go into changing our potential energy. So our initial height and our final height are different because of the fact that this work is going into changing that. For the sake of this problem, I think it makes sense to call the original height 0 meters. So we can say that's at ground level. And up here, where it reaches its highest height, would be 3.2 meters. Okay, this makes it convenient. This agrees then with our displacement of the positive 3.2 meters in an upwards direction. Okay, so let's take a look at how we might go and solve this. Let's come up with a strategy. So the approach that I'm going to take here is eventually I'm going to use the equation that work is equal to force times the distance. The problem is I don't know what force. I do know what force causes the work to be done, but I don't know the force itself. So I'm going to need to calculate that, and to do that, I'm going to need to find the force of gravity. This is the force that pulls downwards, of course. The force applied, which is an upwards, must be equal to this in order to lift it at a constant speed. So I'm going to go over here and we're going to actually calculate this out. We, of course, have an equation for the force of gravity, which is equal to mass times gravity. In our case, the mass was 350 kilograms and G is 9.8 newtons per kilogram. When I multiply these out, I did this on a calculator here, the calculator tells me that it is, I can pull the calculator over here just to show you, Right there it is. It's 3,430, and this would be in newtons. Now, this gives us, of course, the force, the magnitude of the force of gravity. The applied force is going to have to be equal to this in order for it to move upwards at a constant speed. Okay, so basically for the work equation, what we're going to do is use our work equation. We're going to substitute in the appropriate forces for each part. Remembering that for part A, it was the work done by the object lifting it, and for part B, it was the work done by the force of gravity. So for my first one here, this is going to be the applied force, and when I substitute my numbers in, I'm going to get the 3,430 kilograms times the distance it moves, which was the 3.2 meters. And again, this was positive because it was up, and this is also up, so that's positive. So basically we get a positive times a positive. Let me bring my calculator in here, and we're going to take the 3,430 times that by 3.2, and we end up with, for the work, I already forget what it is. Let me go back and look at it. 10,976. 10,976. Let me look that up again. 10,976. There we go. 10,976 is the work done by the applied force. In this case, whatever is doing the lifting. Now over here, when we do the work done by gravity, work done by gravity is going to be very similar to this. Gravity force was the 3,430 times the 3.2. Now the displacement is positive because it's up, and the gravity is negative because it's down. So, of course, if you understand how math works, you'll know that basically these are the same two numbers. The difference, of course, is the negative. So my work done by gravity will actually just be the negative value of the value that I got before. So to respond to our original question, the object, whatever the object was, it does the lifting, does 10,976 joules of work, and gravity does the negative value of that same amount of work.